if you want to follow along on the original PDF.
Okay, very good. The content boxes all came up again.
Yep. Okay. So if people want to follow along, there is a separate link on the PDF for the HamSci 2021 session, for the iPoster sessions, and if you want to click on that link so that you can open up separately in your web browser a different window, uh, you can very easily follow along with the original poster presentation that has been created here. Okay.
Okay, okay. I'm going to start my presentation then. Welcome to my presentation of IONSOUND HDX Turbo, which is a Skywave propagation prediction software program for amateur, professional, and military applications. I am Jacob Handwerker, IONSOUND's author, and my amateur call sign is W1FM. I will try to summarize the 7 scrollable content boxes in this iPoster presentation, consisting of 1, the background, 2, solar, wind, and space weather, 3, diurnal variation, 4, IONSOUND HDX Turbo software predictions, 5, IONSOUND HDX Turbo software manual, and 7 is the examples of hourly worldwide signal-to-noise predictions. This will also feature how IONSOUND can be made available to each and every one of you. The IONSOUND HDX Turbo software presentation covers the 1.8 to 30 megahertz MF and HF frequency range and evolved since the late 1980s and was primarily marketed in the 1990s. So this software is a little dated. It's designed to operate with IBM compatible personal computers using DOS. It can run on the Windows with DOS emulators. This software is intended to produce easy to interpret tabular predictions of RF link performance between any 2 locations on the Earth's surface using transmit and receive location, antenna gain, receiver bandwidth, required signal to noise ratio, transmitter power level, sunspot number or solar flux number, minimum elevation angle from the horizon, prediction frequencies, prediction months, prediction times, and prediction modes involving E and F layer propagation. IONSOUND prediction estimates include total receive reliability, which is composed of the product of path reliability and signal to noise availability, E and F layer ionospheric absorption, polarization loss, and ground reflection losses are all taken into account. Highlights of this iPoster include a propagation overview. IONSOUND software features an introduction to smooth sunspot and smooth solar flux, an extract of an independent science project which explores diurnal variation of time standard broadcast frequencies. IONSOUND HDX Turbo detailed screens and some propagation prediction comparisons are also featured. Shown also is the user manual for IONSOUND HDX Turbo, which gives insight into its capabilities and execution of the software, which is also being offered for free to HamSci participants. Finally, examples of hourly worldwide signal-to-noise predictions derived from HDX Turbo are shown. Summarized in this presentation are the various versions of IONSOUND software developed for use by amateur, professional, marine, and military applications. The standard and pro versions of IONSOUND software accommodated up to 128 frequencies from 1.8 to 54 megahertz and provided simulated ionospheric chirp sounder graphic outputs which in conjunction with the more traditional tabular output provided a unique visualization of maximum usable frequency or MUF and lowest usable frequency or LUF for each propagating mode. The HDX and HDX Turbo versions accommodate up to 9 simultaneous frequencies in the 1.8 to 30 megahertz band and provide a single screen 24 tabular hour summary of frequencies in the 1.8 to 30 megahertz band and provide a single screen 24-hour tabular summary for up to 8 parameters of interest. As background, in 1982, my son Jason became interested in radio wave propagation while attending Lexington High School in Lexington, Mass, and eventually conducted an independent science project titled Diurnal Variation of Ionospheric Radio Wave Propagation. In order to explore the daily variability of shortwave broadcasts, included is an extract of his research, which centered on measurements of broadcasts by WWV in Fort Collins, Colorado, and CHU in Ottawa, Canada, which is also a 24-hour time and frequency standard broadcast station. WWV provided an opportunity for listening to an east-west path from Lexington, Mass, while CHU provided a north-south path. Predictions of how these paths were going to perform made use of the Ionospheric Communications and Prediction Program, or IONCAP, which was a software program that ran on an IBM PC compatible computer in order to provide predicted receive performance signal to noise ratio levels on amateur shortwave radio equipment. The diurnal variation of the 5 WWV HF frequencies and 3 CHU HF frequencies were obtained by measurements during 2 separate 24-hour periods and were then compared with their respective gold standard IONCAP predictions. I should note now that Jason Handwerker is now Dr. Jason Handwerker, and his amateur call sign is N1UEQ. He is also a graduate of MIT and Harvard Med School. It should also be noted that Jason's high school independent science project, Diurnal Variation of Ionospheric Radio Wave Propagation, placed 3rd overall in the physics category at the Massachusetts State Science Fair held at MIT in 1992. Mazel tov. Skywave Technologies developed and marketed several versions of its propagation prediction software. These include IONSOUND HDX, which is introductory in nature and was bundled with one of the editions of the ARRL antenna book. It accommodates the limited locations of ARRL QST's How's the X column during the time when monthly ionospheric propagation predictions were actually provided in the magazine. IONSOUND HDX Turbo added features to IONSOUND HDX, including permitting unrestricted latitude-longitude entries. IONSOUND Standard provided simulated ionogram graphics by emulating the performance of ionospheric chirp sounders during the prediction process. IONSOUND Pro added further features to the IONSOUND Standard version. The transmit and receive location screens of IONSOUND software allow choices for the 14 locations found in QST How's the X column. 7 additional choices not found in the column, manual latitude, and longitude entry, and selection of a file which is user modifiable is also provided. Selected in these screens are Northeast for the transmitter location and Western Europe for the receiver location as an example. Following location selections, The main menu summarizes the current variables in the left column and additional selection choices in the right column. These variables identify the lat long of the transmit location as northeast, the transmit location noise condition as res or residential, the receive location lat long of Western Europe, the receive location noise condition as rural, the transmit to receive bearing in degrees, and the selection of S as short path along with the distance in miles and kilometers. Transmit power, receive bandwidth, receive minimum required signal to noise ratio, and transmit and receive antennas selected are shown. Sunspot number and solar flux number are also displayed, as well as the calculated F and E layer heights in kilometers. Shown also are the minimum elevation angles selected and the calculated minimum F-hops found along with the F-hop takeoff angle. Also indicated are that 8 different 24-hour summary type presentations have been selected. The 8 summary presentations are as follows: total reliability percentage, S meter plus dB, signal to noise, dB microvolts, to angles of takeoff, E and F hops, path reliability percentage, and signal reliability percentage. Lastly, the month selected is shown. On the right side of the screen are options 0 through 18. The default selection is pick a time, display the 24-hour summary, which is option 0, and that allows choice of a prediction time with a default for 24-hour summary. CQ Worldwide predictions for October 1994 to Western Europe from New England are shown. Nancy 6 Bravo Victor, that's N6BV, provided the Yankee Clipper Contest Club, YCCC, the predictions of signal dB microvolts plotted as a function of time for the 80, 40, 20, and 15-meter amateur bands. The tabular summary following the plot summarizes the IONSOUND HDX turbo predictions for hourly total reliability percentage. Shown also in my presentation are the user's manual for IONSOUND HDX Turbo by W1FM, which is for version 3.50. This is the manual that comes with IONSOUND HDX Turbo software. A free copy of IONSOUND HDX Turbo may be obtained electronically, in other words, by email, for HamSci participants upon request from the author. That's me. Send your request with your name, affiliation, and amateur call sign, if applicable, and email address to the email address of Skywave Technologies, which is skywavetech@AOL.com. That's SKYWAVETEC@AOL.com. As a suggestion, please consider a donation to the American Radio Relay League Incorporated. Finally, shown are examples of hourly worldwide signal to noise S to N predictions for the month of November with the solar flux number of 90. These plots are derived from IONSOUND HDX Turbo software and centered on Boston, Massachusetts. Okay, thank you for your attention. 73 and 88, this is W1FM now signing off.
Thank you very much, Jacob, for your fine presentation. I wonder if Scott Driggers from Clemson University is in this room now to present his paper or not. If not, we will move along. Andrew Rodland, KC2G, are you ready to move forward?
Yeah, just give me about 10 seconds.
Counting down now.
Okay. Okay, is the sharing behaving properly?
It's certainly visible to me.
Okay. All right, so good afternoon, everybody. I'm Andrew Rodland, KC2G. I've been a radio amateur for a little over 3 years. I've been writing software professionally for a bit more than 15. And I'm here today to talk about prop.kc2g.com, which is a site that I developed to give mostly amateurs an at-a-glance look of what the HF propagation conditions are. The reason that this thing exists is, like I said, I got started in radio just a few years ago, and I was looking for something like this. I wanted a tool to let me know, what are the conditions right now? What band should I be looking on? Where should I be trying to contact? And so I looked around for resources, and I found a variety of stuff. But a lot of it that I found was not really the best for usability and readability. One of the most popular sites out there that people look at for a muff map, for instance, is literally 640 by 480, 16 colors. So squished and so visually busy that it's hard to read anything off of it. But I found another site that was run by Matt Smith, AF7TI, on his website that had a really sort of nice graphical presentation, and I would visit it on a daily basis. But Matt is into experimentation with his site. He puts different things up, he takes different things down. Eventually he took his map down, and I was bummed because I couldn't view it anymore. And then a few months later, I found his source code on GitHub, and I decided, okay, that's great. I can set it up on my own server. If I'm running it, I'm not going to take it down. I can use it anytime that I like. So I did that, and then I started looking at the code and finding ways to improve it, and I got hooked and have been working on it for the past 2.5 years. So prop.kc2g.com. It is open source. The source is on GitHub, and the data is as open as I can make it. So what is its goal in life is basically to give people access to overview maps like this one that you can see here. And you might think that with all of this data that we have, that creating a map like this would be easy or simple, and it's really not. Although we have access to observations from Ionosphere, which is a worldwide network, but they are not really distributed evenly over the globe, and there's not that much of an absolute number of them, and they're not sending data constantly. They have off times, and they have delays in how long it takes to deliver their data. And sometimes the data is just noisy, and so producing a coherent map from just that is not really a thing that's going to work. We also have computer models of the ionosphere, including IRI, the International Reference Ionosphere. And that thing is pretty impressive. It's the result of decades of work of modeling ionospheric conditions. But yes?
Is it okay if I ask the question now, or I should ask it in the
let me finish first, and then we'll have time to discuss after.
Okay.
Yeah. We'll go through the poster presentation and then take questions before moving on to the next presentation. Okay, Dave?
Yeah. Thank you. Sorry about that.
No problem. But the thing about a model like IRI is it has a limited number of parameters. You tell it what the solar flux is, you tell it what the K index is, date and time, and location on the Earth, and it will give you a climate prediction on average. What's it going to be like for that location, that time of year, that time of day, that solar flux? It will give you the same answer every time. It's not connected to the real world. It doesn't know anything about real world conditions, and there can be very significant variation from day to day above and below the climate. So we would really like to have, the connection to that real world data that we're getting from the Ionosphere. So we would like to connect them, we like to combine them in some way so that, I said, these are my goals. Predicted values, if we have real data, then the values that show up on the map near those real observations in time and space should be pretty similar to the real observations. Far away from where we have data, because, for example, the oceans are basically empty. Nobody is setting up an HF radar in the middle of the ocean. So predicted values that are far away should be consistent with what we see from the real data, and they should be consistent with the models. You shouldn't have crazy discontinuities, and you shouldn't have, just big blank spaces in the middle of the ocean, because, well, you know what, a lot of our propagation paths go across the ocean, and we need to be able to have some idea what's going on there if you want to find out whether or not you can contact Australia. So I overview or outline my computational approach. There's a lot of information here. I'm just going to give the brief outline of it, which is we get our observations from Giro and from NOAA. Giro, I pull the data from their API. NOAA pushes it to me. It all gets stored into a database. And then, like I said, the main parameter that the IRI model is keyed on is solar flux. It takes it in the form of smooth sunspot number. And so rather than use its built-in file of average solar flux for a given month, what happens is I take the recent observations that I have from all of the ionosonds all around the world and feed it into a black box optimizer where I run IRI for different models for different values of the solar flux parameter and find out which value actually brings the IRI predictions closest to all of the measurements that we have from the past day and call that an effective solar flux. And this is the past about year. You can see that towards the end of 2020, things started improving. It's not a great improvement, but we're out of the minimum, and that's nice. So from that point, we have our current value of an effective solar flux, and that's what we're going to use to drive the IRI model from then on. And then we can take, for each ionosphere, we can take the observations that we have from it, and we can find out the difference between what we're actually seeing from that station and what the model says, and subtract them, and then feed those differences into something called Gaussian process regression, which is a really cool statistical technique that is able to deal with trends. It's able to deal with periodic components. It's able to deal with noise components, and you can feed error estimates into the input and get error estimates out of the output that give you a good idea of how confident the model actually is. And as it gets further away from observational data that it can use, it becomes less confident, and it will tell you that. And so this is an example of a plot that's on my site of the past couple days from I forget which station this is, but showing the FOF2, and the blue marks are observed data with error bars, and then the orange is a prediction into the next day. And you can kind of see that the error bars get wider as we get further into the future, because predicting the future is hard. And the reason for this prediction is partially so that you can do forecasting out to the next 24 hours, but much more mundanely just so that you can get a nowcast because all of the stations are reporting on their own cadence with their own amount of latency. So you can be dealing with data that's anywhere from minutes old to a couple hours old. If you were to try to combine all of those into a map directly, then it's incoherent data. So you really want to be able to time align it to a single point in time. So even if you're not trying to look out into the future, if you're just trying to get now, you still want to have a component like this.
Andrew, 1 minute.
Okay. So after that, we can excuse me, apply the same technique, except instead of doing it in time, we do it in space. Take the difference between the model and the predicted values that we have and take those deltas and smooth them and do it in such a way that close to the data points, we get values that are close to the errors that we have, and far from the data points, the errors just kind of regress towards zero. And the result is something like this overview map. It's also, I have a simple ray tracing engine. It needs a lot of improvement. I was hoping to get to this last box, which is some of the future things, because I would like to recruit people to help me with some of these things. There's a lot more that can be done with this, but currently it works quite well to produce overview maps like this for people to view. It's out there, it's in the public for people to use. And lastly, there's a lot of open source software that I rely on to make this work. And this is credit where credit is due. I'm not going to list it all, but it's all in my presentation. Thank you very much.
Andrew, Kilo Charlie 2 Golf, thank you very much for a wonderful presentation. I know that I think Dev Joshi had a question, so go ahead, Dev.
Yes. So the poster you are saying is not available on the link, right? The link is half-filled.
I'm sorry?
The poster, this is implementation of a point-to-point ray tracer, right?
Yes.
And the link that I'm looking at does not have the poster. The link that I'm looking at does not have all the boxes filled up.
Okay, try reloading it because it's all there.
Oh, okay. Despite which it doesn't show up, but
Okay,
I have another question. Okay,
yeah, I think you're looking at the link for the previous session that wasn't presented.
no, it's room 3 iPoster. I'm in room 3 iPosters.
Right, and it's on props.kc2g.com.
Oh, anyways, okay, that's but the question is like I came a little late and I want, you said like you looked somebody's source code, like whose source code was it, like whose idea are you implementing here?
Most of it is mine, but the genesis of it came from Matt Smith, Alpha Fox 7 Tango India.
Yeah, Andrew, do you have a GitHub repository or anything like that with your code?
I do, and if you open my poster, there is a link to the GitHub in the introduction section.
Good for pointing that out.
And would you still help me with getting to the your like full-fledged poster iPoster here?
Sure. I will drop it into the chat and you can find it there and we can move on to the next session to not hold things up.
Yeah, that's a good idea.
Thank you very much, Deb, for your insightful questioning, and thanks again, Andrew, for your presentation. So far, I have not seen Alexandre, Takio, Kitagawa, PU1KTA. That sounds Brazilian to me. On this session, are you here or are there some other guys? And otherwise, if not, we will move on to Robert Westphal, DJ4FF from the Deutsche Amateur Radio Club. So thank you, Robert. Go ahead.
Okay, thank you. I'll share the screen.
Oh goodness, it
So-
looks like me. I'd much rather see your poster. Thank you very much.
Okay. So the title of my presentation is Geocaching in the Ionosphere, which is kind of strange, or seems kind of strange. And the subject is amateurs work in emergencies and emergency calls. So we had an emergency without an emergency call, and there had not been too much amateur radio contribution in the past. What I'm talking about, it's the disappearance of flight MH370 about 7 years ago, which is the greatest mystery in modern aviation. And so I thought maybe we can contribute something besides all the other experts from Inmarsat and other fields that did not prevail until today to find the wreckage of MH370. So how could we do that? Maybe for the first time in amateur radio history, we could step into the past, into 2014, and use WSPR data, which was stored in the WSPR database, WSPRnet.org, since 2008. So there we will find the data for MH370 as well as the SAR operations weeks later, in addition to many other air accidents from AF447 Air France, MH17, German Wings 9525, and many others. So what might help us is that the doomed flight of MH370 happened pretty close to the peak of solar cycle 24 in April 2014. So the problem is now that we have to know how to do that. And I have three categories to look at, which is observation, validation, and verification. So if we start with observation, I do that in the present, not in the past. So we detected some aircraft in Antarctica. So maybe you wonder why I choose Antarctica, because as you probably know, the HF has not, the antennas have no good direction, and just to avoid ambiguity and other things, I choose Antarctica because normally there are not too many aircraft down there. So we did some testing with WSPR, and but we need a reference to evaluate the WSPR data, which are ADS-B data from Flight Radar 24. And I choose a path going directly over Antarctica at about 180 degrees, which is the German WSPR station EP0 Golf Victor November, like the Georg von Neumayer Station 3 on in Antarctica. And as a receiver, we discussed that in the other sessions. Here comes an SVL, shortwave listener, ZL 2005 SVL. Why did I choose that path? Because normally there is not a good, or not at all, a connection between those two stations, Trans-Antarctica. So now we go to the, let's say, the methodology, and here we see some very different things that I did not initially expect. So what I say is the data at WSPRnet.org, they are so-called secondary data. So WSPRnet.org only records those data that have been decoded. But as you can see from the following images, and I cannot go through all of them, is if you have air scatter involved with WSPR, these signals get influenced in shape, in SNR, and in the so-called drift rate, which we measure in hertz per minute. And if the drift rate is bigger or larger than 4 hertz per minute, plus or minus, the signal will not be decoded. So for example, in figure 1, you see just normal WSPR signals, straight lines, waterfalls at KVSDR in Perth in Western Australia. But if you go down and, for example, here, this is not too bad at all. We received VK2 EFM with a strong blip of some kind of reflection or scatter in the beginning. But the waterfall is still straight. But other things can happen as well. Let me take a very bad one. Let's take this as an extreme. So here to the left, here now you see VK2 EFM is strong. There's probably air scatter involved, but there is no drift on this signal. But to his left, there is a signal which has a very strong drift, much larger than 4 hertz per minute. So it will not be decoded in the system. You will not find it in the whisper database. And this is probably due to heavy banking of an aircraft leaving airport Melbourne after departure. So on and on. And also we have, for some reasons, whisper signals will not be decoded, but if we use, and I proved it with the Kiwi SDR network, if I have a bilateral or multilateral reception, for example, in Indonesia or in the Philippines, and it will be detected at one of those locations, and I can assess what kind of station it was. So to summarize on that one, we lost redundancy in the WhisperNet database. So just about examples, I see maybe this one is Mark yesterday, who is down at the McMurdo station. Of course, I had also many flights going to McMurdo, and I think I also have, I don't know if it's in this column or not, we will see. I have his 17A Globemaster 3, maybe down here, I don't know. He has a so-called joy flight from Qantas, going from Perth to here. Is an Ilyushin IL-76 TD, and here is from the Australian Antarctic Division, the Airbus A319 going to Hobart in Tasmania from Wilkins Aerodrome. Here is an Argentinian C-130H, and here we go. This is the airplane. As Mark used it yesterday, C-78 Globemaster 3, coming back from McMurdo, flying into Christchurch, CSPHT. And those flights were taken for detection in Whisper. And I cannot show all of them here. Here we have a flight QFA 114. It's one of those rare flights, repatriation flights during COVID-19. And the special thing about it is just goes through the estimated, last estimated position of MH370, about 2,000 kilometers west of Perth. And we had all kinds of signals received from South Africa into Australia and vice versa, but also signals along the Great Circle paths from Costa Rica and Mexico. So why Costa Rica, for example? Because if you make a really big Great Circle into America, because you end up at the longitude of 93.8 degrees west of Australia, which is the estimated longitude of the final position of MH370. So what did we achieve so far? We have here, for example, for MH370, if you, I cannot show that here, how that flight went after it became invisible on the air traffic control. But we made a U-turn at 1722 UTC. We received a signal from Thailand HS0ZKM at VK3DXE down by Melbourne just about that time of the U-turn when the flight changed heading from going northeast to Beijing to flying northwest. We also have a change in signals at Singapore Station 9V1TD, and this chart, for example, shows a mid-course signal, mid-course with Israeli station 4X1RF receiving VK3DXE at 2120 UTC, and the blue line is the estimated flight path by doing the math on the Inmarsat calculation. Those 7 pings from the Inmarsat satellite are the only proofs that this flight was in the air for hours. It's just seven pings, but with Whisper we have about 8 hours of data. But it's a little more complex to get the data we're interested in. And so by the end of the flight, which is here, we have VK6ZRI, a silent key in 2017, receiving VK7FI, and on the left dot in the sea, 2,000 kilometers west of Perth, is the estimated last position of MH370. So it's most interesting if there had been reflections by the ionosphere or not. With Propagation 3.1, we did some calculation if it's possible that with ray tracing we could reach that airplane, and it is. So the final phase of MH370 I address at 8 several clusters, such as in the vicinity, like VK6ZRY, VK7FI, and a signal to Thailand, but maybe that was flight VK425. Then receptions of signals in the west of Australia and New Zealand, analysis of signals on great circles from Venezuela, Uruguay, Paraguay. There has been a whole bunch of 20 strong 28 megahertz signals on maybe short pass and long pass. We have to look at that. Then also some strange and weird signals from Réunion, FR5, and Cameroon, TJ3, which make no sense in the first place. And then the analysis of signal paths on the great circles, and maybe others which have yet to be identified. So in discussion, I think Whisper is a very versatile system, and we could support the other data from Inmarsat hydrophone detections, aircraft debris, and military and civil radars. Whisper alone, I think, will not be able to locate the wreckage, but if we do data fusion with all the other data, it might be possible. But we need, and we are in urgent need of more ADS-B data, not from MH370, which are not available, because it was invisible, but from other aircraft in the region of Oceania. So we already have some and enough flight data where I think we can prove some conspiracy theories wrong, but we're not going into details. One of the next steps will be maybe also in the southern hemisphere, look at SuperDARM, the Chinese radar ZHO, looking north, and maybe 2,500 kilometers will not be far enough. I looked again, I found some blips between 22 and 23 UTC at 3,500 kilometers. I think we have to look in more depth into the SuperDARM signals. We have the signals from the search flights for QFA 114, and we have to with hammer radio amateurs for further investigation. And we are in urgent need of more ADS-B data. So in conclusion, I think Whisper is suited for that job, and We can detect the flying aircraft after under certain conditions and certain space weather. Aircraft spotting has been demonstrated in Antarctica over thousands of kilometers, to 7,500 kilometers. And in addition, as a side effect, other whisper stations could use that effect to enhance their radio range by scatter wire aircraft or even the ISS if they have poor antennas. Aircraft whisper detection is also feasible in the back or in the past until 2008, as we can use the whisper database, whispernet.org. Further investigation of the ionospheric influence on this process is absolutely required. We need more reference data for locations, such as the ADS-B data, and for the region Oceania in March 2014. We use propagation tools such as WarCap and PropLab, and we have to look at further depths into the mid-course and the final phase of the flight. I think amateur radio can provide a great toolbox in order to achieve faster solutions for possible future cases, because air traffic control is still not able to detect and track long-haul flights without any active location transmitters aboard the aircraft. Still, stealth aircraft are still unvisible at present. So we have the same problem as 7 years ago, and it could happen every day again. Whisper non-detect should temporarily at least have to be stored in the Whisper database for 24 hours to 1 week for optional analysis in the case of a future emergency, such as MH370. And further installation by radio amateurs, as you plan to do it, with the PSWS, space weather monitoring, remote SDRs, as Kitty SDRs, ADS-B receivers, etc. By the way, we could only do that in the second half of 2020, because before that there were not enough ADS-B receivers in Antarctica. So even the IRU could build, let's say, an AMOMS system, an advanced amateur object monitoring system, to do all that. And if such a case would happen again, to find a wreckage or a plane much earlier than in the past. So we could monitor space weather, whisper reception, and a ready-to-use alert system can be provided on an adequate system for ham radio under the supervision of IRU and deployed in the near future, just in time for the 100th anniversary of IRU in April 25. And maybe such a minor system like multiple input, multiple output system with a connection, a mesh connection, not just point-to-point connection as we did in the past for 100 years, might be even attractive to modern, what I call smartphone kids, internet kids, geocaching, gaming, and video kids. So maybe this is one way of doing amateur radio in the next 100 years. So I think that's it, and thank you very much.
Well, thank you very much, Robert, for your fine presentation. Are there any questions before we move on to Michael Zurich? You'll have plenty of time to chat afterwards. Robert, go ahead.
Well, I've done, I think.
No, so again, thank you very much, Robert Westphal, Delta Juliet 4 Fox for your fine presentation. Moving on to
Thank
Michael
you.
Zurich, Nancy Tokyo 6 Victor. Are you ready to present?
Sure. Robert still needs to close the screen share so I can share my screen.
Okay.
Okay.
I can probably force it, but I'd rather not.
It's like in the robot, it's in the center of the top of your. It's in the center of the top of your screen. There's like a red thing. You have to
I see.
Yeah. There you go.
All right. So my presentation is going to be rather brief. So we'll basically just talk about our. Can you actually see the screen?
Yep, your presentation is live and visible.
All right, so that's 599, I guess. Well, awesome. It's great to be here today, and I want to just briefly introduce our activities at the Berkeley Amateur Radio Club, Whiskey 6 Bravo Bravo. So that's right here on campus at the University of California, Berkeley. Again, it's just one overview of activities we do. We don't have like any scientific kind of oriented results to show this. Hence, I will keep it kind of brief so you can look through it later. So if you're interested on the history on amateur radio here in Berkeley in the west part of the US, our club is around since more than 100 years. And there's a long history of getting on the air and having on-campus activities, or some, if you're interested in like old-timer photos, so there's been like all sorts of equipment installed over the years, and quite a number of activities, and hundreds and dozens of hams have been going through here to study and get active on the air. One thing we recently do is basically that's came out of the COVID-19 pandemic is that we kind of thought we need to somehow overhaul our shortwave station that we have, and that is a station we have at an offsite location on campus. So as you may have heard, real estate here in California, especially the Bay Area, is like really expensive, and it's densely populated. So we're really happy to have an offsite location that is like near the San Francisco Bay, where we can have a really decent shortwave station where our students can get on the air and where we can experiment with SDR and all this. And the station has been QOB on and off since 2008. When the pandemic hit, we realized it's going to be really hard for our students to actually get on the air and get active. So what we did is we installed like a fully remote accessible station using Elecraft equipment and commercially available equipment to completely remote control the station so that students can get on the air from at home. If any one of you is interested in details, I'm happy to share and talk about it. So basically that's what it looks like. So having an amplifier K3 that kids can operate from at home in all modes and get on the air and FD8, CW, whatever they like to do. So that works fairly nice. If anyone has questions about how to do that, I'm more than happy to share all the information. That's a photo of our shack. So we have a nice little shack there near the bay, and currently have a Yankee antenna up at 20 feet, and we use that for like contest activities, generally propagation studies. So we use that station also a lot in instruction. So if you're interested in academic instruction and run ham courses, so that's all something nice to do actually. So I'm giving a sophomore seminar in the spring right now with about 20 freshly licensed radio amateurs who are all like, early semester students here, undergraduate students in engineering, physics, chemistry related subjects mostly. And what we do is, since we teach online now, basically I have like a control head here for this K3, and I can basically run the radio from my home office here and share like the audio signals and all that with the students at home. And so we can do propagation tests, and it's just you go in 40 meter CQ and then check on reverse Berkeley network where the signals are being received and so on. So it's a very practical way you can get students engaged with practical aspects of amateur radio. And that's something we developed and do quite successfully. Just a few words on instruction. So basically right now we're having two courses. So the first is a freshman course that's run by Professor Mickey Lustig. He's an engineering KK6 MRI. So he teaches a course hands-on on ham radio, which is basically, if you will, if you think like that, like a license course for obtaining technician license or general licenses. So the students actually get a full semester of basically teaching on the basics of amateur radio, and they take the amateur exam as course credit. So we have about 40 to 50 new technician and general licenses on campus every year. And I'm happy to also share that about half of those are actually women. So we have a pretty good representation here across different populations on campus, which I think is great. And then I myself, I teach a second semester course, a sophomore course, which is called Fun and Ham Radio, which then consolidates that, where we then basically say, okay, now you get a license, but what next? What is the next thing we can do with that? And we touch on a lot of topics like, how to build a station, how to design antennas, and, a little bit of RF design, how to build an antenna practically, traveling, building your own equipment, contesting moonbound, satellite use, radio propagation. And that's also a lot of things we heard today in the session are actually quite really intriguing to me as well to hear what other peoples are interested in doing. So we're using, for instance, VOA Cap as a website to kind of illustrate, like takeoff angles and then how does this link to antenna design if you like want to reach a certain area of the world. So we teach that to the students and show practical examples using our remote station. So this is how this ties together, basically theory and experiment, if you will. And yeah, so that is essentially a few things, and you can read the post online with a few more examples what we do. Maybe more interesting from a technical perspective, if you haven't heard about that, that's maybe something quite interesting for the community. I know that the HamSci community also develops their own SDR, and probably it's very tailored to the needs of that community. Something we did install when we redid the HF station last fall was we got a Red Pitaya StemLab SDR. If you haven't heard about that, it's a pretty neat small device. Actually have a picture of what it looks like. So that's the SDR. Has 2 antenna inputs for receive, and what it does is it does provide 2x8 190 kilohertz wide receiver slices on amateur bands between 160 to 6 meter. It's basically continuous reception, so you can basically listen anywhere you want. But basically what you can do is you can say, well, you can set up a total of 16 192 kc wide slabs of band that you basically stream through gigabit Ethernet to, like any HDSDR or any kind of software you like to listen on a certain band or run automatic receivers. So what we use it for is, and my main motivation was actually I wanted to have a local receiver since we're here the west coast of the US and quite far away from like a lot of the population centers of the world where a lot of hams are. It's kind of like when you want to get on the air and you have like a modest station like we have it, it's always kind of nice to see what's going on in your location, what you are being hearing with your antennas. So, of course there is like, PSK reporter and reverse speaking network for CW and all that, but often, other stations have other antennas or different noise level. And so for us, it's often nice if we can just really flip on the radio and right away see who is being heard by our own station. So that was the motivation to install this as a basically band surveillance system that captures CW signals and FT8, FT4, and basically gives us a local representation of what we hear in our antennas. And of course, we also feed these signals to the networks, which is, I think, important for those being interested in the data and accumulating, information. So just so to introduce how this works. So basically, or what is possible with this kind of SDR. So what we do in our station is we basically run CW skimmers, so basically decoding CW signals on 8 bands simultaneously on 2 different antennas. So that's a total of 16 CW receivers. So basically, one antenna is a 3-band Yankee that you just saw in the picture, and then we also have a low-band Beveridge receive antenna that's about 200 feet long, works quite well on 80 and 40 meters to get some signals on the lower frequencies. And so that is basically simultaneously decoded. So this gives you a total of 16 receivers. Then we use a bunch of software. If anyone's interested in that, I'm more than happy to share all the details and give you a rundown what to do and how to configure all that to get it to work. And basically, on top of that, we have on each of those receivers, we have 2 more receivers for the FT8 and FT4 subbands and run instances of WSJTX on each of those receivers. So what this means at the end of the day on this one hardware, we're running a total of 48 receivers that automatically decode CW, FT4, FT8 on 8 HF bands and listens on 2 different antennas at the same time. And so that is operational. And works. We also here in the Bay Area, just to share that kind of technical insight, we have pretty strong AM broadcast stations right by the San Francisco Bay. So if you ever come here, you will see there's a ton of like really tall towers right by the bay. And that's a lot of the West Coast, AM broadcast is being transmitted from here. So that is an issue if you want to do like shortwave reception and you have like these broadband receivers with like less protected front ends. So there's a way, of course, you can add some filters. We did that, bought a bunch of filters from Mausers and put them in that helped big time to really be selective on the ham bands. So if anyone wants to know how that works, I'm happy to share like the details of that as well. And yeah, that's basically what we can report on with that simple box we built. And it's basically queued in with the K3 transceiver. So basically it always listens on the same antennas as the K3 is on. So we basically always have a full representation of the bands. So we're listening on, and basically you can click on those links on the poster as well to see what we're hearing right now. But don't know how exciting it is for you guys now. But for us, it's kind of nice to see where we are listening to and what kind of signals we're hearing in a certain time. And it's also nice to show the students, like, you know, how the bands open up at different frequencies throughout the day. And you know, it's kind of neat to say, okay, that's really our own station hearing that. Yeah, that's all I have for you today. Open for any questions, of course.
Yeah, quick question. Do you have difficulty getting students to the remote site since it's off campus?
No, it's that's actually the point is, I mean, it's a remote site, and that was one of the points that I want to make. It's like that we built the station fully remote, accessible through the internet, because it's actually hard to get there. It's an offsite location that has its own security and police and everything. I mean, you know, it's a bit of crazy place out here in some parts of the Bay Area. So it's just fully protected, and each student who would go there has to be signed up by us. So the campus affiliation isn't enough. You have to be signed up and cleared from security, and then that's a hardship, and you need a car to go there. It's an offsite location, so you don't want to take a bike and ride there. It's a bit of sketchy area overall. I mean, the sub campus itself is just fine, but, like, you know, the surrounding is a bit sketchy.
Yeah, well, there's so much of the East Bay area that could be described that way. So, from wo sind Sie, Michael?
Oh, I got here from Germany, so my other call sign is Delta Golf 1 Charlie Mike Zulu. So I immigrated just recently.
Oh, okay. Well, you know, welcome. I spent 2 years living in Vienna and working for a small Dutch light bulb company, Firma Philips, back in the mid '80s. So.
I mean, I can show you all because of access to the station, and, you know, then you would think, like, students, they need all the control equipment, and it's all something we took care of. So we have this Pelican cases here, and that is what students can check out, like a book in the library, basically. And these Pelican cases, what they have inside is basically everything you need to operate these stations. So, like, power supply, and you have, like, these Elecraft K3 control heads. You know, that's not a radio, that's just a control head, and you basically, students can take it to their dorm, plug it in the Ethernet board in their room, and basically they're on the air, you know, and they can check this out.
Exactly, that's what's called a K30. I have one myself and have used it on the remotehamradio.com radio station network, among others, and with my K3. So
very good. I learned to contest W6BB many years ago, and when it was in Corey Hall, and you've got to have a better antenna location than that.
Yeah, no, that is true. And the Corey Hall shack still exists. So we have basically two shacks. One is on campus, and the other one is at the San Francisco Bay in the offsite location. And the campus location suffers from QRM so badly. So we have, like, you know, there we have a flags, and we have, like, a multi-band antenna on the roof of Corey Hall. But basically all across the band, the noise is S7, S8, S9. It's basically unusable. It's too much computer stuff and HVACs around on the roofs, and the campus is just a mess as far as electronics go. And that was one of the motivations when I came here to campus. So I was like, you know, we have to get a decent shortwave station where we can actually hear something, because if the students, you know, they get their license, then you try to motivate them to get on the air and get active. And then the next thing you know is they try to go to Corey, tune the transceiver there. They don't hear anything. They are not being heard. They are not getting out. Also, you need power here. 100 watts is nice, but, you know, if you just want to call CQ and also have someone answer, it's better if you are near the legal limit. You know, you're far away from a lot of places. So that was the main motivation, like upgrading the station, make it decent, that you be heard, that in the contest you can actually make a few contacts, maybe have a small pilot going. And then at the same time, the concept of saying we need equipment that the students who don't, you know, they are short of money all the time. So we have to give them everything they need to get on the air.
Yeah.
And so they can basically go to the library and check out this Pelican case and, you know, take it to the dorm for a week, get on the air, sign with the call sign, their own or club call sign. And we also think about doing contest activities this way, that we can kind of pass around the remote station and use, like, Slack to interact and say, okay, now you take over and run a bunch of QSOs. And Yeah.
So Corey Hall is roughly what AGL feet or meters? I don't care which.
Oh, HEL, I mean, it's 300 feet.
Yeah,
but it's tucked-
at best with severe hills and mountains to the east.
Exactly. We are tucked in right below the Lawrence Berkeley National Lab in the Berkeley Hills.
Yeah, we had great path to Northwest Asia, but continental US was tough from there.
May I interrupt?
Yeah, sure.
I need to go shortly, so I thought I would check if anybody has any questions for me before I need to leave.
Okay, so any final wrap-up questions for any of the previous presenters? I've been unable to see that Scott Driggers or Alexandre Takio Kitagawa have shown up to present their papers. So, I mean, otherwise we'll be on to just continued general discussion on various and open topics once Michael's wrapped up.
Yeah. I'm disappointed that that Scott Driggers didn't show because I was interested in that topic.
And I'm sure others were too.
Yeah.
So that being said, I mean, I think we're pretty much on to this breakout room is really no different from any of the other, however many that Nathaniel has set up. And although it has a name, and we started here to hear a certain collection of papers, it's pretty much onto a general discussion. So feel free to unmute your mics and carry on with discussions of topics of any mutual